In this video, we're going to go ahead and tackle some advanced topics, really a single advanced topic for radical expressions. A few prerequisites here. Solving quadratics, you have to know how to solve a quadratic equation, what it means to solve a quadratic equation. Also, you should know how to simplify radicals, and you should know all about exponents, laws of exponents, negative exponents, all that fun stuff. We'll first start with a little recollection that if you're given a quadratic equation, ax squared plus bx plus c is equal to 0, then we can use the quadratic formula to solve it. Normally I would recommend not using the quadratic formula, instead trying to factor first, but when all else fails, we can use the quadratic formula. So you have this possibility of getting a radical in your answer. As a simple example, we'll take this. Now this hopefully does not factor. I don't think it does. We could try to see if it does. Then I would have created one that is absolutely factorable, which it does actually look like I did. Now that I'm looking at this, this does factor to 4. All right, so I'll change my numbers here. I'll change this to a 7 in the center. That goes to show you, by the way, that I do not try my examples before I write them up here. I just hope, cross my fingers and hope. Anyhow, if you were to try to factor this, it would not factor. So we're going to just immediately go to the quadratic formula. The quadratic formula says that x would have to be the opposite of the b value, which is the coefficient on the x to the first term, plus or minus the square root of that b value being squared, which will be 49, minus 4 times the a value, which is 2, times the b value, c value, which is 2, all over 2 times the a value, which is 2. And when you look at this, this becomes, negative 7, let me clean that up, plus or minus the square root of, well, let's see, 49 minus 16 will be, I think, 33. Let me just do the math in my head really quickly. 16, yeah, this looks like 33, all over 4. Now let's actually zoom into this a little bit more just to take a look at what's important here. That becomes negative 7/4 plus or minus the square root of 33/4. And there's something significant about that. So our solutions are x equals 7/4 plus square root of 33 over 4, and x equals 7/4 minus square root of 33 over 4. They're almost the same answer, except for they differ by that sign in the center. One's positive, one's negative. These are known as conjugates. What a conjugate is, well, you essentially start with a binomial, a plus b. If somebody hands you a plus b, the conjugate of a plus b is going to be a minus b. And if somebody hands you a minus b, well, the conjugate of that is a plus b. So all you're doing is switching the sign in the center. What's interesting about the quadratic formula is every answer you're given using the quadratic formula actually gives you conjugates, even if they're not involving radicals, actually. Remember my mistake I wrote up there a few moments ago, and I said, oh, actually this does factor, right? This factors 2x, let's see, x, and let's see, this becomes 1 has to be 2, so that's going to be a positive 2, and this is a positive 1. Okay, so this factors a 2x plus 1 and an x plus 2. You could double check that, but it actually does factor in that. So the solutions here are x equals a negative 1/2 and an x equals a negative 2. Well, written like this, you can't tell that these are from a conjugate pair, but had you used a quadratic formula here, you would be able to tell that there are conjugates going on. This is x equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a, right? And so this becomes a negative 5 plus or minus, well, that's 25 minus 16, or the square root of 9, all over 4. And there's a couple ways you could, well, there's a really good way you could write this as a negative 5/4 plus or minus 3/4. Or in other words, you have two solutions. One is negative 5/4 plus 3/4. the other one is negative 5/4 minus 3/4. Notice these are conjugates. This binomial is a conjugate of that binomial. So these are conjugate solutions. Like I said, the quadratic formula almost always actually gives you conjugate solutions. There is a special case where it doesn't, and that's when the radical turns into 0. But we're not talking about that right here. Now, what does this have to do with all the radical stuff we've been doing as of late? Well, quite a bit. You can see that from our previous kind of sub-example here, that if I can guarantee 7/4 plus the square root of 33 over 4 is a solution, then 7/4 minus the square root of 33 over 4 must be a solution. Now let me write that down. The theorem goes like this: if x equals m plus the square root of n, or some type of radical, is a solution to ax squared plus bx plus c is equal to 0, then its conjugate is also a solution. And that's the advanced thing we're doing here, is if I give you a solution to a quadratic equation, you should be able to tell me what the other solution is, and you should be able actually to build back the equation. So let's try that. So let's show that negative 3 plus 3 root 2 is a solution of the following quadratic equation. And then after that, let's go ahead and state another solution to that quadratic equation. To show that this is a solution, we're just going to plug it in. We're going to let x equal a negative 3 plus 3 root 2. That's how you show that something solves an equation. There we go. We originally had something squared plus 6 times something minus 9. And we want to show that that's equal to 0. Right now we don't know if it's equal to 0, but we're going to eventually show that it is. Inside those parentheses, we'll put negative 3 plus 3 root 2. So negative 3 plus 3 root 2. This first thing is saying negative 3 plus 3 root 2 times negative 3 plus 3 root 2. That's what the first term is saying. The second term, I'm just going to distribute that 6 to each of the terms inside the parentheses. So I'll get a negative 18 plus 18 root 2. And then minus 9. And we still want to know if that is equal to 0. Well, let me multiply out this binomial, this set of binomials here. Negative 3 times negative 3 is a positive 9. Negative 3 times a positive 3 root 2 is going to be a negative 9 square root of 2. Positive 3 root 2 times a negative 3 is a negative 9 root 2 again. And 3 root 2 times a 3 root 2 is a positive 9, and the square root of 2 times the square root of 2 is a positive 2, so 9 times 2. And then minus 18 plus 18 square root of 2 minus 9, and we still want to know, is that equal to 0? Well, let's see. This positive 9 will cancel with that negative 9. Negative 9 root 2 and another negative 9 root 2 becomes a negative 18 root 2, but we're going to cancel that with a positive 18 root 2. 9 times 2 is positive 18, which cancels with this negative 18, and we get 0 on the left-hand side, which is actually equal to 0, so that checks out. Now that we know that's a solution, another solution would be its conjugate. So a negative 3 minus 3 root 2 is the other solution. So we have two solutions, negative 3 plus 3 root 2, and then once we know that's a solution, then its conjugate must be as well. That is almost technically it here. I suppose I can make one more, not super challenging, but just interesting problem. Let's suppose, let me go to a new page here, and let's suppose that we have the following solution to a quadratic equation. Let's suppose that x equals 2 minus the square root of 3 solves some quadratic equation. Let's find a quadratic equation with this solution. And the reason why I put a, not the quadratic equation with this solution, is because there are an infinite number of quadratic equations with this solution. We're just finding one of them. Well, I know that if x equals 2 minus the square root of 3 is a solution, then x equals 2 plus the square root of 3 is as well. Now here we go. We have these two solutions, which means that if you subtract 2 from both sides of this first one and add root 3 to both sides of that first one, it means that x minus 2 plus the square root of 3 is equal to 0. That's what the first one means. The second one means that x minus 2 minus root 3 must equal 0 as well. Now what I'm going to do is build back the quadratic equation. So this tells me that not only is this first object 0, but this second object is 0, which means that if I multiply those two objects, I will get 0. So if I multiply x minus 2 plus root 3 and x minus 2 minus root 3, that should become 0. Now all I have to do is multiply all this stuff out. There's a couple ways you could do this. I'll show you kind of a long-winded way, and I'll show you a really cool, fast way. Long-winded way is to distribute each of the terms in the left factor to each of the terms in the right factor. So I'm going to go ahead and do that. And I'll do a colored distribution. In other words, I'll take x in black here and distribute it to each of these objects, each of the terms over here. And then I'll do -2 and distribute it in blue. And then I'll do the root 3. And the root 3 I'll distribute in red, maybe. So the root 3 I'll distribute to each of those as well. Alright, let's do the black stuff first. X times x gives me an x squared. X times a -2 is a -2x. And then x times a negative root 3 is a negative x times root 3. Notice how I write that in that order. I didn't write root 3 times x. Reason why I do that is because often I'll see students do this, and it's hard for me to tell if they want the x underneath the square root or if they don't. So I tend to write the variable first. One of the few exceptions to those writing variable second rule. Now a -2 times x will give me a -2x. A -2 times -2 is a positive 4, and a -2 times a negative root 3 is a positive 2 root 3. And finally, distributing the root 3, I'll get a positive x root 3, a negative 2 root 3, and finally a -3, right? Because root 3 times root 3 is just 3. And one was positive, one was negative. And that's all supposed to equal 0. Let's combine like terms here. So now I'm just going to be in green. I'll just have an x squared. Let's see, a -2x, lose another 2x. So I'm at a -4 of those x's. A negative x root 3, but I'm adding back an x root 3. So those two cancel, actually. So I'll cancel those out. A positive 4 minus 3. Positive 4 minus 3 is going to give me a positive 1. Let me cancel out the other stuff that I've actually already taken care of here. And then finally a positive 2 root 3 minus 2 root 3. Those cancel out. So my equation just becomes this. X squared minus 4x plus 1 is equal to 0. Now I told you I'd show you kind of a neat way to do this. So that's the long-winded way, taking each term on the left-hand side and multiplying against each term on the right-hand side. And there's nothing wrong with that. But let me show you kind of a shortcut. If somebody gave you a problem like we were working on, it's always the case, actually, that you can kind of group things like this. X minus the quantity of 2 minus root 3. Notice if I distribute the negative, I'll get a -2 and a positive root 3. So that's exactly what we want. And then the other one is x minus, and again, 2 plus root 3. Okay? So all I'm doing is just kind of grouping these 2 and root 3's together a little bit. And then when I do the distribution, really I'm only distributing 2 terms on this left-hand side to 2 terms on the right-hand side. I'll show you. This x will get distributed to this x, and this x will get distributed to this picture. And then this picture will get distributed to x, and this picture will get distributed to this picture. You might think, well, that's a lot of math still. It actually does reduce down quickly. X times x will give me an x squared minus x times 2 plus root 3, whatever that may be. And then in red, I have a negative picture times x, or in other words, negative x times 2 minus root 3. And a negative times a negative will be a positive 2 minus root 3 times a 2 plus root 3. And this is what's kind of neat about using this method, is that this right here is actually a difference of squares. It's not really a difference of squares, but we can see the pattern. Remember way back when we learned like x minus y times x plus y becomes x squared minus y squared? So we could use that here. So watch what happens. I get x squared minus 2x minus x root 3 minus 2x plus x root 3. So you kind of see the cancellation already. And over here, 2 times 2 is 4. But then I'll get a positive 2 root 3 and a negative 2 root 3. Those will cancel out. And then negative root 3 times a positive root 3 is a negative 3. So it is a little bit faster if you can see the pattern. And like I said, the x root 3 positive will cancel with the x root 3 that's negative. And you combine like terms and you get x squared minus 4x plus 1 is equal to 0. Same answer. So it's just a neat way to approach this problem. Anyhow, that's it for the advanced topics for radical expressions.